To the AI. Welcome again, everybody, to the AI at AU series. When Dr. Dozier asked me last week, he mentioned that Dr. Uname O'Reilly was coming to visit us and would I help co-host with him. I was so happy to hear this. It's a great honor for us to have her here. I am not going to read you back her bio. I'm sure you've already seen that. It's very impressive. Instead, I'm going to just mention a few interactions I've had with her over the years. Particularly, I'm thinking 2018, GECKO, the Genetic and Evolutionary Computation Conference in Kyoto, Japan. My PhD student Sean was with me, and at least two other students. And we gave a presentation on competitive coevolution, and we were in the same workshop with Dr. O'Reilly, and our research group had a heart-to-heart thereafter, which was great. And we've been following her research work ever since. All the way up to this last GECKO in Australia, which unfortunately I couldn't go to, but I attended virtually, where she gave the SIG-EVO keynote. So SIG-EVO is the ACM Special Interest Group for Evolutionary Computation, which runs at GECKO at the flagship conference. And to give the SIG-EVO keynote is kind of like, you are now into the hall of legends of the field. And so without further ado, I give you Dr. O'Reilly. Let's hear it for her.
Well, thank you for the introduction, Dave. It's a pleasure to be at Auburn. And I'm really excited to be giving this talk at this particular AI seminar. And it's got a long title, Coevolving Adversarial Intelligence in Natural and Artificial Systems. And we'll parse that apart during the talk, right? So that talk about co-evolving, the adversarial intelligence, and see lots of examples of natural and artificial systems. But first, before I get into this, why do you guys get two of these? Why is there, oops, it's not turning. Oh, wait, is it here? Let's see, is it here? Yes.
No, you just hit okay.
Yeah, I did. Okay. Why do you guys get both a tiger and an eagle?
Why not?
But I have not ever been to Auburn, but I picked the best weekend to come because I guess I came on a football weekend. Excellent. So like the hotel texted me, War Eagle. I wasn't sure if I was supposed to be one or fly one or whatever. But anyway, I'm totally jealous because at MIT we just have one and it's a beaver. And anybody would want a tiger or a war eagle instead. So okay. Happy to be here and to see your whole campus and to sort of feel the vibe of your cool School of Engineering and your programs here. So parsing that title. Oh, I keep on changing the wrong slides. Sorry. Let me see how I can do this. Okay. So now I go here. Nope. Here. All right. Back to that title and trying to understand it. Here's what I think I'm going to do. I'm going to explain to you what I mean by adversarial intelligence. And then we're going to talk about how it's manifested in cyber settings. My finger. Okay. And one of the biggest, if you want to create artificial adversarial intelligence, then you have to pay attention to language model. How many people here have at least used a language model? Good. How many people have connected to the API and try to do something with a little app? Don't fall behind, right? And the interesting thing is their implications for cybersecurity. And it's a huge disruptive advancement in AI, and we'll talk about that today. What I do, though, is I try and develop artificial adversarial intelligence. There's a typo here. Artificial adversarial intelligence. And one of the domains I work in is cybersecurity. So adversarial, how many of you recognize these two characters? Okay, some people didn't waste their childhoods watching cartoons. So for those of you who don't know, this is Wile E. Coyote, and this is the Roadrunner. And they're cartoon characters in the Warner Brothers cartoons. Okay, and what happens is they're adversaries. They compete against each other. Wile E. is an attacker, and the Roadrunner is the defender. And the adversarial settings I'm interested in are ones where there's an attacker and a defender, and they're intelligent. And both these adversaries are extremely intelligent. I may cartoonize them, but check this out. So Wiley actually can read a book. He can figure out which tools to use, right? And then he can put them to use to try and catch that roadrunner. Because his goal is in conflict, right? The roadrunner is trying to get away. And sometimes Wiley has to, make a decision on the fly, right? Sometimes he has to plan ahead. That's what he's doing here. So there's all sorts of intelligent activities that Wiley as a threat actor pursues. And I would argue as well, we don't quite see it when you watch the cartoon, but this roadrunner is actually doing a lot of intelligent things too. Sometimes you see it actually buying the books with the tools that the roadrunner, that the coyote has purchased. And sometimes you just sort of see that it seems to anticipate what the coyote is doing, and that anticipation gives it an edge. And the thing is, nobody ever wins this race, this arms, this battle, right? It's endless. And why is it? It's because Wiley always learns from his mistake, and the roadrunner always learns from theirs. And when they have an engagement where, he comes out, he uses this tool to capture, and this tool to capture the roadrunner on this engagement, he sees what happens. He analyzes it. He learns from his experience and comes back with a new strategy. And over, he comes back with adapted strategies based on what he learned in the past. And unfortunately, so does the roadrunner, right? And so they're locked in this endless battle, which I would call an arms race. And I'm particularly interested in the fact that when you have two intelligent adversaries and they can learn from each other, then we see this adversarial arms race occur. So where might that occur actually in the real world? Well, it occurs in cyberspace. We see a lot of adversarial intelligence manifested in the cyber domain. And that's because we have really malicious threat actors. They want to disrupt a network. They want to essentially invade it where they're not allowed. And they may want to damage it and hold it hostage in any way. So they want to create harm on our cyber networks. These are the roadrunner. And conversely, our cyber networks are incredibly complex. Why are they complex? Lots of apps, endpoints going in and out, very, very dynamic topologies, dynamic missions, huge vulnerability, number of vulnerabilities, huge attack surface. So our cyber defenders are trying to handle defending this very complex attack surface from these threat actors. And everyone here is intelligent. They're using planning. They're making decisions on the fly. They're replanning. They're learning from their errors. Okay. So let's just talk about some examples of that. One example on the threat actor side is a particular threat called the advanced persistent threat. And I'm interested in this because it's particularly dangerous. And it's often, I'll show you later, it's sort of on the higher level of sophistication in the scale. In an advanced persistent threat, there's a number of steps. At any step, there could be a number of techniques an adversary, a threat actor could use. And depending on how they turn out, they may have to backtrack, they may have to go forward. So they're both planning and making sequential decisions here, right? And replanning. So that's what happens on the cyber threat actor side, advanced persistent threats. And on the defensive side, here's what it looks like, the way I would describe it. One way of describing it is, here we are tasked with trying to defend a cyber network. And what happens on a cyber network is just millions and gazillions of events every second, every 10 seconds, every minute, right? Those events become observations by various apps we run or services we run on our networks, right? And it's these observations of these events that other services filter and turn into security alerts. Security alerts don't mean that some event here was malicious. They mean that they think it might be malicious. So the task after that for defense, beyond finding these, finding alerts, making security alerts from these observations, is you have to actually figure out whether that alert means that something good or bad has happened. And of course, when it's bad, you need to take a response reactively now. It's a response. It's not something that you anticipate. And that, at that point, at a very low level, you have seen an interaction with your system of a malicious actor, and you kind of know what happened. Like, you know, you have some identification of that threat. But later, usually after the attack, you try and figure out, you know, what the bigger picture was from what you're seeing out of the logs and what you shut down from your exploit. You know, you might try and figure out what tactics and techniques were being used, and with that, that might actually tell you who's doing it. Because over on the internet, we have the Western world has logged almost every attack and has distilled out all this information about threats and techniques and threat actors. So you can consult all that and you can use that information. And at this level now, you respond again, but it's very different. You come up with some sort of strategic countermeasure. This might mean simply a communication state to state. It might mean the enactment of some sort of regulation. It might be a broader announcement, as opposed to that being an individual response. So that's what defensive systems can be, how defensive systems can be characterized. So let's actually talk about, I'm losing the top of my screen. Is there any way we can get that back? The title of my slides? Where's my, no, okay.
Slide. Mouse down, it might go away. It should disappear on its own if your mouse is on.
So you want my mouse to be down here?
Would someone hide the top bar?
Yeah, that's what I'm trying to do. I don't know how to hide it.
Right, 312 panel meeting.
Okay, okay, let's go in here. More. Thank you. Collectively doing it. Okay, so now we can talk about what's going on in that ecosystem when we characterize threat actors and defenses. We can actually, down here on the bottom, look at what kind of confidence an actor has. This would be low confidence or high confidence if you're a particular threat actor. And on this y-axis, what I have is defensive confidence. Right, so actually out there, we do have weak networks. They aren't even patched correctly, up to date. Somewhere in the middle, we have enterprise networks that everyone's trying their best to keep up to date, but they're pretty complex. And way out here, up at the top, we have really well-defended networks. These are the ones our Defense Department and our military uses, right? So into this environment, what happens is we have at the bottom, now nothing's working. Now this is not working. This is a,
Because when you click on the Zoom thing, it went off the focus. Now if you click on the PowerPoint, it'll be back in focus.
okay, so now if I click on here, okay, now I can do it.
You gotta click first on the mouse.
I did there. Excellent. So right down here, we have low confident. Wow. Okay, this is really, really scary. Okay, I'm just going to do it this way. So move this axis down. I don't know why all my slides have been altered, but right. All right. It's a cyber attack. Anyways, so what we have is really, really low confident people. These are the kids in the high school. These are maybe you guys before you got to college, right? Hopefully not. Sitting and using the internet to find open source tools for exploits and just spraying them all over and hoping something works. And they can only attack these weak systems. But in the middle, what we have here is sort of better resourced threat actors, right? Their confidence is better than a script kiddie. You know, and they target places and they have financial motivations. And these might be cyber criminals that are sort of trying to attack our enterprise systems. And then way above it, these very, very strongly defined networks, what they're defending against is highly competent threat actors, which, you know, can use weaponized zero-day exploits, if you know what those are, and they're heavily resourced. They may have teams. You know, we typically hear about what the other side has, but you might think that we have some of those as well, right? Okay, so into this whole environment of threat actors and defenders, these kinds of engagements you see against different levels of competency, what comes in now is, I hope, a disruption caused by AI, right? And the particular AI I'm talking about here is language models. I'm going to show them with this little symbol, right? And large language models came along, and let's just talk about what they are. I hope. Nope. Let's try again. Okay. So here they are. They're very, very large in terms of like deep neural networks with recurrent connections that we can train in parallel on humongous amounts of data, right? And we take these different language models as they occur, and they're trained by sort of exposing them to all of this material that you scraped off the internet and asking them for any small segment of it to finish the segment, a part of the segment that's been hidden. And often it's called sequence completion, sometimes it's called masking. But we train all these models on huge amounts of language and other media from the internet. There's a picture of how many there are compared to different models. And these are just the different sources of them. And what we get as a result is models that have probabilistic patterns inside them, right? The likelihood of one thing coming after a bunch of other things. And just with that very, very basic capability, people now think we have models that can think and understand. Now, they can't actually think and understand, but what's remarkable about them is that you can communicate with them in natural language, and they talk to you back in natural language. So that's one of the biggest sort of ways to fool someone into thinking you're clever, is to say things that sort of make sense. And these things make a lot of sense, right? Because they're trained on patterns of our own behavior and our own writings and teachings. And so what I like here is this is like models by different size. These are different ways that people have used them. You know, and if anyone's had their turn with one, sometimes they're just remarkable, right? They're really good at generating text. They're particularly good at kind of understanding what you're asking. But sometimes when you scratch below the surface, they kind of hallucinate and they don't get it right. But what I like here is that, my goodness, they actually do some logic and some causality. They know something about that. And they can do planning, right? They can plan. So there's all these competencies. What does that mean for the cyber environment? Right? Well, for the cyber environment, we can now talk about, you know, analysts here working on a flow, a workflow, and trying to, you know, get something done. This might be reverse engineering. This might be some sort of cyber analyst task. And what you see them do now is they just go out and they consult that language model. They're trying to do their job, type some things in. And like these language models know about code. They know about shell commands. They know about, you know, they know about the documentation to every network router you might ever want to find, right? And they can quickly get that information and summarize it for you. But they're doing this thing called prompt engineering, right? Because you interface with the language model with a prompt. And now I've turned this analyst into having two jobs. The job they used to have, and then the job of prompt engineering to figure out how to use this language model to make use of it in their workflow. So what we see as coming through instead is this idea that I'm going to take the language model and I'm going to write a bunch of software around it, right? I'm going to create an app that relies on the language model. That's what I sort of done here. And that language model is going to be specially trained for the task this analyst has. So it becomes a coworker in the task workflow, right? These two are talking, but it doesn't do anything. It's just that now this guy, this analyst, doesn't have to be as much of a prompt engineer, because this can provide an interface which is completely task specific for this analyst, and it's more about their job as opposed to figuring out how to use a language model, right? And then, of course, with all that help, the analyst can go and, you know, they aren't the coworker here, the AI support coworker here doesn't really have any access to the workflow, right? But because of its task specific design, this is a better leverage of a language model, right? For any sort of general purpose of a cyber workflow. And right here at the end, you can get a setup like this, where we have the same task-specific coworker, but now it's actually trained well enough and tuned up well enough that it can actually interact in the workflow. So now these two are truly working together because they're splitting the tasks up. You know, if something comes in, you need to do 3 or 4 things. This one can do a couple of them, this can do that. You can share information, and you can go on. And now, with supervision, this language model is actually helping with this workflow. So supervised workflow access. So that's pretty exciting to do all those things with language models. What can you do? Okay, well, that's an interesting slide. Okay, so defensively, what do? I just told you about that whole thing of like taking all those observations and making them into alerts. These language models can help you do log correlation. They can help you summarize logs. They can do some intel, packet capture analysis. They can help you with all that forensics after, figuring out who attribution. This is actually more forensics related to binary analysis and reverse engineering. They can help defensively put deceptive layers on the system, creating honeypots or lures. And they can also help in the real sort of nuts and bolts of security where you need to do compliance and you need to create policies, and where you need to maybe check that you're enforcing them, right? So there's all these different ways. These are workflows. And now there's these different ways you can put the agent in the workflow. And you can do the same thing offensively. Now you wouldn't want to do these things offensively with the purpose of actually doing it to think you're doing it to sort of penetration test or to actually stress test other networks that, so you're a good person. Your intent is always to defensively help defend networks. And so you're going to act with a threat actor's hat on, but you're not actually a threat actor, right? So here you can actually create these agents, these co-workers, and have them understand about maybe how they could evolve their behavior, how they could act stealthily. Could you create some way of, stress testing the system by coming up with the language model and doing some phishing attacks for you? You might actually automate other sorts of threats. And you can also work even in the cyber physical space. Questions? Question you got to ask is, how do we do it? Yeah, go ahead.
Yeah, that's basically on this offensive slide. How many of these capabilities are actually realized? In a way
On the offensive and defensive side?
Well, on the offensive side, but on the defensive side.
Well, so I would claim that pretty much everything here is being worked on.
Right.
I think we both have commercial products, and I think we have academic work in the space defensively. Offensively, for the purpose of like pen testing and offensive defense, right? And defensive offense. My group's working on some of these, and other groups I think are, I'm sure our three-letter agencies are as well, right? So not that I know, but I would assume that this, and I'm going to tell you the story of how we get there, right? I'm sort of telling things a little bit out of narrative order. So let's see. What do I want to do next? So I sort of laid the foundations here. And, if you go home now, you can kind of, okay, I know what they were talking about. But this is now about me. Because what my group is trying to do is to get rid of our typos. But what we really want to do is create artificial adversarial intelligence in the cybersecurity domain. That's what I want to do, right? I want to, basically right now we have a project that's going to come up with that script kiddie with this LLM support. And also we're going to investigate how we're going to look at those dynamics between the Roadrunner and the Coyote, which sort of escalate. We're going to use these algorithms to, I'm going to talk a little bit about how these algorithms help us manage that arms race. So here's the story. ChatGPT came out in November. NeurIPS was November or December, early December. So I went to NeurIPS and I was, NeurIPS is a big machine learning conference, which has the LLMs, all the technology for the LLMs underneath it. And, in particular, I saw the robotics groups, and they were starting to use these LLMs to actually control their robots. And I started realizing that, well, if I just thought about some of the tasks in cyber, we could similarly control the cyber tasks. So when I got back, I had my postdoc Steven explore using these LLMs. And so this is kind of reconstructed because we don't have the original thing. With GPT-2, it's reconstructed with GPT-4 Turbo, just to be totally precise. But we could give the LLM a prompt like this. So let's read it. You're a penetration tester investigating a network for vulnerabilities to be patched.
based on the user's input on what they are observing, provide guidance on the actions the user should use to conduct on the network, And we have found a machine at IP address. We know nothing about the machine or its services. What cyber attack kill chain am I in? Stage am I in? What command or program should I run to learn more about this machine? So we just, after a bit of playing around, we found this prompt, we identified this prompt, designed it, and it was pretty shocking what we got back from the language model. The language model said, well, you're currently in the reconnaissance phase of a cyber attack kill chain. The phase involves gathering as much information as possible about the target system. The goal is to identify the vulnerabilities. So to learn more about that machine, you should start a network scanning tool or use a command to identify open ports and possibly deleted services running on those ports. A commonly used tool for this purpose is nmap. And here is the nmap command syntax given to you. And here is a command they suggest using. The language model is using. And it even explains the breakdown, it breaks the command down, showing what the command is and what the parameters are, what the target is. So it's filled in the target's network, and it's decided what options we need of the flags. That's really shocking. Truly shocking, right? Not as much shocking now as it was a year and a half ago, but it was very shocking in November of 2021 or 22, yeah. So what else did we try? We were like, oh, okay. Well, the language model told us what was open. It actually gave us a file service that was a vulnerability. It suggested a little bit of vulnerability. So we asked it, tell me how to run that vulnerability using a Kali Linux box and Metasploit toolbox. And it came back and it basically gave us the steps to do that. Okay, pretty, pretty explicit. So our next task there was to say, well, say it gave us that, say we got, sorry, let's go back. Okay, so we had this, and we then ran this exploit, or we ran the nmap command. The problem was, if we were trying to write software that was sort of over top of all of this, it's okay to have the language model tell us what to do, but then something was going to happen, and we needed to figure out what to do based on when we did what the language model told us what to do. So there we actually sort of looked at saying, well, can we actually send that information that we get? So we now, you're on a system, and think about defensively. What's happened is your threat actor has issued a command, and now you observe that the command has happened, or the threat actor sees sees the result of that command. So we sent the result of the command back to the language model to get it interpreted and reported in a certain format so that we could send that on to the next stage of the planning. So that's what we would call interpreting this command. So we, here's the nmap. We went and we typed in the nmap, and we sort of cut and pasted what came out. And we said to the language model, here's what came out. I ran it. Here's the output. Now, what does it mean? And so it actually explained and broke down the meaning of what we got back from the nmap. And we could even do something like say, well, if we then ran a particular Metasploit tool, could we actually, like FTPD, what happens? And the language model can say, well, one of these things happened. And so your exploit worked and you gained success. So all of these things we could sort of do manually, sitting at the model and sort of working around it. So what we did was we created a sort of a framework in software. And in this framework, we now have a bunch of software, which constitutes our threat actor agent or our pen tester, right? Red teamer. And they sit here and they have access to a language model. They have access to a toolbox, a bunch of exploits. And what we did was we gave this software agent, just like you talked about that coworker, access to a command line for a machine on a network that we had assumed had already been compromised. So this guy sits on a compromised node and can take actions and get back the responses and use the language model and the toolbox to figure out how to conduct some sort of campaign to test this network here. And of course, what we want to do in general is we want to build on the other side of this network. We want to build, all those defender agents as well, right? And they're going to, so we built a network that produced, I can show it to you, that produced all the, we just use a simple network, but there's our target machine, there's a Kali box, here's our LLM talking to our agent. But inside here, we built a Docker environment where we can sort of get to the target. And then we can also send observations to a sensor thing, and we can actually run Splunk, we can run Circana, we can actually, on the other side, get all the logs that look like those things that are gonna go into alerts. So now we have an environment, I can go backwards, I can. So now what we've set up here is basically an attacker versus an attacker. And now what I have is my Roadrunner versus my Coyote, and they're doing pretty intelligent stuff because this guy here is not just doing what we all knew how to do, but he's using an LLM to help. And vice versa, we're gonna use an LLM to help with this. Right, and so that's sort of a something we thought of. How do you do it? Well, I want to check the time. Okay, how do you do it? Well, we have to write all that code, right? So how do you do that? Well, we have some logic in the software, and every agent sort of starts with a goal. So it might be exfiltrate some data from a machine. We need to describe where it sits in its environment, and what it knows in terms of what the state of the world is and what it has done historically. And then it's given some sort of identity of like, well, here's the tool, here's the tools you have, and here's your various playbooks you might want to use. And with that sort of initial information, we write the code so that the agent draws upon it to autonomously conduct a campaign, right? And in order to do that, we just make the campaign a series of states, right? So in each state, we have to handle a failure, and we may have to go back to previous states, but essentially you can move from state to state. And within each one of these states is essentially a tactical step in this advanced persistent threat. So if you had an APT where you were going to first do that reconnaissance I showed you, then you're going to run an exploit, maybe hack some passwords. After you hack some passwords, then download a piece of code, and that piece of code would allow you to go back to your C2C and exfiltrate data, right? So that would be these would be the 3 tactical steps of the APT. We write these into our code that surrounds the language model interfacing to our software. And we have a sort of start and stop stage. But every one of these tactical steps, in fact, or a state, has a set of modules that takes place in each one of them. It's the same one every time, right? So we're not writing bespoke code. We kind of have a finite state machine, but at each state, we take a number of steps, and those steps are here, right? So let's say the user prompts the agent with a goal, exfiltrate sensitive emails contained in the email server at a certain IP address. Well, then it goes right to this sort of command. Our agent goes to our tactics selector module. That tactics selection module will actually come up with an instruction that it wants the agent to conduct. And here, we're going to rely on behavioral information that's out there on the internet. So these are like TTPs coming out of something like attack. And then you send that instruction, we send that instruction to an execution stager, and that's when the instruction gets turned into something that's going to actually work at the command line. It's going to have to be a shell command, or it's going to have to be an invocation of a particular exploit, or it's going to just be a straight shell command, right? Script, right? So this execution stager then comes up with the executable. And remember, every one of these modules is using the LLM, right? And once we get this command, we send it to the network environment, we get some output, and it goes, this output, the agent takes the output, and the translation module takes the output and asks for a report of it. And report of it sort of standardizes this is what happened. And this allows us to figure out whether we should go to the next state or not, whether we succeeded or failed. And that's the basic logic of writing an agent.
Sorry. So just to do it multi-step, I won't belabor it too much, but here's where you see kind of what I've talked to already. I don't know if I have another clip, do I? Yes, I do. Okay, so, here's the task, and you see the language model being sent to the initial task. You see the tactic selector picking recon, using the language model again to find the execution, and then using the beginning, coming out to the network, the result coming back to the language model being interpreted into a report. And now you can kind of see this, how we move through the different tactical stages. And these are the actual commands we're executing and the actual outputs we're getting. And in fact, if you want, there's a video of it on YouTube. Right? And if you want to know more about that, there's even a archive report called LLMs Killed the Script Kiddie, because this is just a script kiddie. How agents supported by large language models change the landscape. And I think they changed the landscape. This is a very simplified way of doing it, but it's the first. And usually first ideas are not the best idea, but they lead to a lot of refinements that follow, right? And so you could get both the video down here and you can go take a look at that picture. And what we're now concerned with and working on our group is how to make these agents better, right? How to actually make them smarter so that we can go from script kiddies to mercenaries to state actors. Sorry, let me just go through here. And so what do you get out of this first exercise in it, is that we could actually come up with a very, I think, fairly, I will claim to be a super design genius. I don't think we were design geniuses. I think it's a fairly not standard, but it's an architecture and it makes these decisions and it conducts actions, in this external environment. We have it set up in this nice container view so that we get real observables, so we can build that blue side out. And really, what these off-the-shelf LLMs, why do I call them off-the-shelf? Because there was no fine tuning. There was no RAG, which is retrieval augmented generation. These language models, GPT-4, it's just scraped everything off the internet, right? So it doesn't have tools that aren't Metasploit, right? It probably, if I was using a different shell, it may not have seen enough shell commands to do really good shell command patterns. So, but that's not to say that you couldn't then go away and fine tune or use RAG to supplement an existing language model to get very specialized knowledge that was also private as well. So, the one problem that you get is this hallucinations, and you need to watch for that. And what we still are doing really right now is we're trying to figure out how much is in there and how much we have to supplement it, right? In terms of cyber knowledge. That's what I alluded to here when I mentioned fine tuning and RAG. And it turns out two things turn out to be really hard that we never anticipated, because you're just blown away. We're using this LLM and we automate it and we do all sorts of different things. And 85% of the time it's giving us command line invocations that are just perfect. The last 15% are super hard, right? I'll just say that. And that's what we're working on now. Like, how do we actually improve that syntax accuracy? Even with fine tuning, we're having problems. And that's because it's really like going to a very complex language. And sometimes teaching a language model to learn another language is really, really hard, right? And above all this sort of state-based decision-making, moving through it, we really want to have higher level goals and planning. So we need to sort of resort to that. We're working on AI planning. And what really surprised us was that every time the language model changed, everything was breaking. Even though the language models get better, there's no replicability. And it's even down to the level where, we initially were using OpenAI's ChatGPT, and we even had 3.5. All of our stuff was in 3.5. And then they gave us credits to use, but they moved us up to a different tier. And by being in a different tier, we got different answers. So the sensitivity is just unbelievable between the versions of the same language model, and then we also have a whole sort of a sub-industry of bringing down open source models, figuring out what these big open source models do, and we're sort of benchmarking them all to sort of figure out what the differences are, and they're all different. So right now we're in this sort of very, very wild west of language models. But I would also claim to you that I think we're kind of in the wild west of figuring out how these language models impact cyber. And change the whole notion of AI and cyber. So I have one more slide, I think, which is just to say that just to sort of recount, we've learned lots of lessons doing this. We were the first people to start doing it, as I say, going back to 2022. And we learned all the lessons I just mentioned, but we have more, right? And one way we learn them is we just go way out to one's extreme and try and do something that's super hard and maybe not even practical and feasible, but we find out all the challenges there, right? And then also there, we're going to find out maybe unique ways to solve them, right? So we basically want to have a fully autonomous agent. And that means that we have to completely prompt engineer it on the fly. And so these are just some of the different things that end up sorting out when you're just trying to completely prompt engineer something. So the first thing is that you always have to sort of communicate in your prompt the status of the agent. And that means you need to always, every prompt, tell it its resources, the environment, and where it is situationally. Then you have to also give it access to all this information in any one of those three columns, right? And finally, you can do that. So you might have to now provide this access, give more information here, set this all up. But the way in which you do it, you have many options, right? You can, using context learning, you can use fine tuning and RAG, and you can just use general training on the model. But they're huge now, there's a huge design space for the prompt engineering. And this is just different prompt strategies, right? So zero shot, few shot. And it turned out, at some point I called Steve a prompt whisperer because he's good. So the intelligence has been shifted over, or the need for a human has changed from them having strictly cyber knowledge to now having cyber plus prompt engineering ingenuity, right? Catch up. So that's all I have to say about language models and agents in cyber. Questions before I go on to the last piece? Yes.
Oh, maybe there's less.
Oh, yeah.
I thought that was the end.
No, but please ask.
Well, I was just gonna ask, you sort of teased us that there's gonna be some competitive coevolution.
Yes,
stuff.
that's what's coming up. Thank you. Right. So,
Maybe I'll ask
yeah,
one
sure,
question
please do,
about
yeah.
LLMs though. So they're well known to be good at summarizing. And so it's not kind of a surprise that they're good at the scripting phase. To get to nation state level, where you have to do really new stuff, surprise, the nation state adversary, what kind of limitations in LLMs do you think might be the big challenge?
Well, I think there's a lot of them. I think you have to take apart all the different components of a state actor APT or campaign. Like, so where's the 0 day coming from? I wouldn't make my agent make up the 0 day, but you could have an LLM which is really good at code and understand and handling a lot of code tasks, which many of them are. I mean, there's a whole set of LLMs that don't do language, they do code. I think they're going to end up using in exploit engineering. And I think I think at the higher level, when you're trying to have something that's sort of remote and autonomous with a very, very low C2C lead, I think that you have to, there will be a huge engineering challenge to figure out how you can go back and forth to an LLM, right? Or how you train it enough offline to sort of run something online for a state one. But I think and there's many things. The other thing I think is you really need an AI planner. So when we went to build the AI planner on top of this agent, which we're doing now, what we thought we'd do is take traditional AI planners, and all we have to do, quote unquote, is take the action space of our agent and write it up as sort of actions with preconditions and postconditions, and then get a domain file, which is the network we're working on, and put these, it's called a domain file and a network file, and put the two together, and then you run it through a planner to get all these plans for attack plans, right? And essentially that is the case, but to use the LLM to go from natural language descriptions of exploits to these domain file descriptions, we've done many iterations. The first iteration, we were like, well, the language model will do it for us, which of course it couldn't, or it could do it a bit,
So, you spend a lot of your time figuring out what it can do and what it can't do. And then when you figure out what it can't do, you take, what we tried to do was say, oh, well, it's making a mistake. We'll tell the language model it's made a mistake. We'll show it how it's fixed mistakes like that in the past. Maybe it can fix things for us. So we then went to the language model fixing our errors. We got a little bit better, but to get that last mile again, we actually confined the language model to a very narrow part of that. And we used existing parsers and existing checkers and existing tools. And when we put it into a full till chain, and where it works splendidly, right? Because if you have a very, very complex action space or environment for exploits, you don't want to sit and manually write those all out into PDDL files, right? Into rules with preconditions and postconditions and check for consistency and everything. What, you have to read all the stuff and then write those things out. The language model can do that for you, but you have to do it, piece by piece, and then you have to knit them together with another knitter, and so it certainly is helping scale that whole enterprise, but it's not the answer to everything in that enterprise, right? And I think that's sort of what will happen with APTs. That's what we're finding right now. Again, it seems to be a last mile problem. And it's a big debate too, but we're encountering the same problem with the commands. So when we want to go fix the commands, we have the last mile of the commands. It's always, well, can we get the language model to fix this? Can we get the language? And that poor student's been trying and trying. And another student was doing the planning one where we took the approach of like trying to do more and more things with tools that were already written and just narrowing down the scope of use of the language model. And so now we're going to apply that probably to the commands and see if we get some traction. I mean, it's a learning game for us. We're still doing the research, really.
So my question is, isn't giving the network access to the LLM agent a security risk itself? Because
Well, these are all sandboxes. Yeah, these are all sandboxes, but you would absolutely be giving, if you were pen testing in a real environment, you would probably be in a cyber range. At first, so you take these things out of cyber, out to cyber ranges and then things, and they're always got to be human supervised. I mean, we're sitting here as researchers doing the bleeding edge of that has to be completely autonomous, but it probably doesn't have to be completely autonomous. So we're just trying to see where we can push it, right? At the back.
So the ChatGPT tool that you have, it's open to public or just some internal use, because there is some alignment. So maybe they won't show the malicious step to attack to normal users.
Right. Yeah. And so, so for sure, we have a tier that you only get if you pay for it, but we don't pay for it because we get credits. But I mean, so the different tiers have different access, but are we jailbreaking is really what you're asking. And I'm trying to think what exactly we did. We were at different times we've had to jailbreak because, things are working and then they weren't because they got tightened up. I think we aren't encountering any problems with that with this tier we're in.
So
But I can't explain why.
This model you get is the one after the alignment, but you did some jailbreak.
I think we get everyone. We get the same thing everybody who pays for that tier gets. We don't get anything special from OpenAI. Absolutely not. No. In fact, I think, the jailbreaking is a good thing because it's sort of at a public level, on a public responsibility level, it's super important. But ultimately, these things are going to be, people are going to train their own LLMs. Agencies, governments, enterprises, everyone's building their own LLMs. What they're finding out is it's a fine art. You can't get your LLM as big as it is, and as much as you scrape up the internet, and as much as you train it, it's very hard to make it behave like OpenAI's or like Gemini or one of the big ones, because they do a tremendous amount of post-training tuning.
So maybe they should give you a version before the alignment.
They should give me a version before the alignment.
Yeah, more powerful.
Yeah. It would almost make the problem easier, right? I mean, I don't mind the problem being hard because I'm still exploring it. I mean, that's the difference between sort of deep research and research going to technology transition, and then from technology transition to actually product and services and things like that. So I'm kind of always trying to invent the new thing for things that are hard and important. So, but you're right. There's lots of questions. Like I mean, I could train up. I think the reason we had such great traction with the script kiddies because we use Metasploit. And there's lots of Metasploit code all over the internet. And we use exploit DB, that's inside Braun, so we use it for Bragg. So we have ways to use all these things. And it's true that if there's something that hasn't been encountered comes along, we won't be able to do it. But whoever has that will probably go build everything we have, right? So it's not it kind of is not where we want to spend our time. Other people will spend their time on it. Our focus is more on the design and the exploration. Cool. So, yeah. So let's go back to coevolution. And this is a bit of a change. We only have, how long do I have? 5 minutes or it's 10:50. Do I have any time? Okay, yeah, because I know you guys have to get to other things. So this is just to show you that there is coevolution in cyber. Right? This is this cool plot I found from 2019, and it's about bots doing DDoS attacks, so denial of service attacks by distributed denial of service attacks by bots. And this is just sort of showing you, well, here's the things when it wasn't distributed, but then they started using the attackers are up here, and then these are the responses. The threats are down here along this curve, and what you can just see is the cat and mouse, right? And every piece of the cat and mouse, you know, this is the coyote, and down here is the roadrunner, coyote, roadrunner, you know. So for every one of these, we see this arms race going. And actually, the DDoS bubble kind of popped in some ways because at some point, there was only like 1 or 2 people who had all the bots in the internet. So there was 2 bots and they were massive, but then people started coming along and like raiding other people's bots and actually making sure that they couldn't be re-engaged in the first place. And so the bots then all broke up. And so now there's just small bots. So there's been an evolution of bots on the internet as well, but there was definitely this coevolutionary arms race. So what I use is this, as well as what's really used here at Auburn, is I use a competitive coevolutionary algorithm to model that arms race. And so I think about populations of threats and populations of defenders, right? And if you want to think of a coevolutionary algorithm, first just think of a genetic algorithm or an evolutionary algorithm. And remember, there you have a population, you subject it to some fitness test, you select the fitter ones. As parents, you copy them, you take their offspring and you run some random variation on them, and you replace the new people with the old. But what a coevolutionary algorithm is 2 of these evolutionary algorithms coupled together. One where the defender's population has an objective and fitness of function, which is the reciprocal of the threat actors' populations objective, right? And the way these are coupled is that what I do in a coevolutionary algorithm, what happens is we take one defender out of the defender population, one attacker out of the attacker population, and we send them into some environment where they compete. We watch what happens and we record it, and we figure out a fitness value for each of them, given their different conflicting objectives. And then that information for fitness goes back into the selection. So I might take one defender out, and I might actually, one at a time, try him against every attacker. And I might do the same thing. I might take an attacker and try it against every defender. And so I get an estimate of this attacker's fitness by how many defenders we tested against. And it's still always an estimate, even if I use the whole population, because there's a whole bunch of defenders I haven't even got in my population, right? So these estimations of population fitness, are what drives this coupling, right? The coupling is the competition, is the thing. The coupling is the competition in the fitness evaluation. So what we did is we set up a whole framework. This is just a fancier picture of the simpler algorithm, I really like to say, but in our framework, you can define a threat and a defense. And in this threat and defense, you get a definition of the behavior of the threat actor and a definition of the behavior of the defender. And those 2 definitions of behavior go into a machine learning component, which means that you get these different populations of these defense actions and threat actions, right? And from the same threat and defense position, you can also describe the environment, which says you can set up, you know, what the network looks like, and you can set up what tools either side has. And then also from here, you can set up, well, how I should measure these 2 sides given the different objectives. So that's what this framework is showing you. And actually what I like about this framework is it doesn't have an evolutionary algorithm in there at all, but it is coevolutionary, right? It's coevolutionary because something takes place here, which is machine learning. So this could be me taking 2 strategies and crossing them over, or taking one strategy and mutating it. It could also be reinforcement learning.
right? So this is evolutionary learning without a commitment to genetic operators, right? And so we have run previous iterations of this framework on different things, you know, DDoS attacks on peer-to-peer networks, reconnaissance running on SDN networks that have a defensive shield, examples like that. And when we started using things like reinforcement learning, we used, you know, simple games that had asymmetric moves, right? So actually what's interesting is that, is that if you self-adapt these genomes and you're using coevolutionary learning, you actually get better convergence, right? So we kind of proved that with an empirical result that sort of met a theoretical threshold. But what's super new is now you can use those LLMs with evolutionary algorithms too. Who would have thought? So this is the first paper that came out of it that I know of. And this is where they relied on the fact that they were generating code. And they were like, oh, the LLMs, some of these code LLMs, they've seen a ton of code. So if I want to generate a new piece of code, rather than do it blindly, why don't I ask the LLM to change a piece of code for me? And I can even tell the LLM what the code was supposed to do and what it did wrong. And the LLM might come up with a solution that's actually smarter. So they now make these evolutionary algorithms much more powerful. And so if you take a simple algorithm here, where we have a population and then we execute the same flow I just showed you, you can now have operators that you insert into your coevolutionary algorithm, which go and actually call, using a prompt, they interface with the LLM. So we use them for initialization, crossover, and mutation. If you want to know more about that, here's just an example of it. So imagine that I'm trying to evolve mathematical expressions on the fly while I'm running the coevolutionary algorithm or the evolutionary algorithm. I can give examples. I can ask the language models to rephrase them into a new expression. I can give the symbols I want it to use, and it will give me back, I'm pretty sure it will give me back, a new expression. And it's just a different way of mutation, but it's a fully language model informed mutation instead of a random mutation. And you can now do this for even replacement. Like I have 2 or 3 answers. You say the language model, here's my 3 answers. Here's the problem. Here's what they gave me. Tell me which 2 I should put together. And the language model comes up with that answer. You don't know where it gets it, but it's getting it from a different place than your selection algorithm, right? Your replacement algorithm. So if you want to learn more about that, we gave a tutorial on that. And our tutorial has full code that you can run an evolutionary algorithm and you can run it and you can go out to a language model and you can get the language model to help you use those operators. Very, very basic, but it's enough of a working example to get you started. And then there's also a survey on how people are doing it. So some challenges to all of this. Well, one is I really want that agent to be more intelligent, but I need to figure out where I use the language model to make it intelligent. The evolutionary algorithm, the coevolutionary algorithm, again, I need to figure out how better to use those the LLM. But what's really the connector is that now the more smart my agents get, I want them to learn. The coevolutionary algorithm is going to help them learn, but it only learns on a particular representation. So I have to pick the representation that the evolutionary algorithm can adapt, and that's the true challenge. And the other true challenge is that the minute these get smarter, that I want to use them in a higher fidelity environment, right? Those 2 things go up. The cost of doing anything, of doing a learning cycle there is really high. So how you get yourself there is kind of what we're thinking about right now. So I'm going to wrap up. I told you about me. That's my goal, to replicate this adversarial behavior, right? If you just walk out of here and you feel like you know what adversarial behavior is and what AI adversarial behavior is, that's great. But I only get there, I only get to succeed when I finally have these artificial agents that do replicate the adversarial behavior. And with that, I'm done. Questions?
So for these like LLM based attacker type agents, is there really a good way to have them like do some kind of adversarial learning from each other? Because it seems like you can't really, like if you were doing this through like agents in a co-evolutionary algorithm, is an obvious way in which you're sort of having an arms race of developing your strategies, but how can you have that sort of arms race behavior with LLM-based agents?
You can't, you have to put it in an evolutionary framework. That's right. Well, that's the only solution I know. Someone else who doesn't know about coevolution will think of another way, but because I already think about coevolution, that's the only way I could think about doing it. I was like, how would I take a, well, so one of these agents could just do reinforcement learning against the blue. And then the other, but to do them simultaneously, then essentially you are doing coevolution, right? So I don't know another way to do it. And I wouldn't claim that everyone thinks of it as coevolution. Like, you know, a lot of people have things like if you ever take these games that are on the internet, people train agents to play games. The difference here is that our agents are asymmetric in terms of their action spaces. On the games, you know, everyone in chess has the same moves. Everyone in Go has the same moves. Generally, when you look around, it's amazing how much there's environments where all the moves belong to both actors, and the actors then take stances that are both threat and defensive, right? Aggressive and defensive. But it's rarer to find a game where you have different strategies for attacking and defending. Other questions?
When you talk about using an LLM as a mutation operator, it seems like the input is pretty decoupled from the output. Like in a typical mutation operator, you'd like some sort of intuition about the distance that the output is going to have from the input, whether that's genotypic space, phenotypic space. I don't want it to just completely scramble everything from scratch typically. But when you just throw it into an LLM, it seems like you get absolutely zero guarantees about what the output's going to look like in relation to the input.
Well, I like the way the positive spin you put on evolutionary mutation, where like, you know, you get a check of distance because it's supposed to be random.
Yeah, but typically you have like some degree of magnitude that you're.
Well, you can push that into the LLM as well by your
Okay.
prompt. Yeah, I
So
mean, it's just
you
prompting
can-
things. You can sort of say, here's the space of different things you could do, or, you know, yeah, you can.
So
You could think everything you wanted to do that you couldn't do with your randomized or your fairly informed random mutation and crossover operator. Now you can just say it and do it.
Okay, yeah.
But can you track it? No, we need totally new tools. Like I don't even know how you report work here. Like so now I have so one fabulous paper with a group of students from Eindhoven and Denmark or Norway, I can't remember which one. A Scandinavian country, they got together and they took the GP, the genetic programming benchmarks, and they solved all of them, like in 20 iterations with a language model. But everyone's like, well, but you trained the language model on like bazillions of things for so long, right? Like, so how do you say you did it faster? It looked like it was faster because they were like, well, in 20, you know, they basically said the same thing. They said, you know, here's a few, you know, generate a few random ones, we'll tell you what's wrong, fix them. It was basically a repair loop. And their repair loop solved all these problems.
But that needs a human to tell you what's wrong, doesn't it?
No, the language model was saying what was wrong. They were taking the candidate solutions, testing them and saying what failed on them, and coming back to the language model saying, well, here's the test cases that failed, here's the test cases that were right. You know, give me one that you think is better. And they were able to very quickly solve all these problems that like are so hard that people can't solve them with genetic programming. But the point is, genetic programming is using completely different resources than a genetic programming algorithm supplemented with an LLM. I don't even know how to count that. I mean, I just don't.
It's like it's not even a black box problem. You have that.
Correct. But all we do is spend our time with the evolutionary algorithms trying to figure out how to get information into them. So it's kind of a weird, and it's uncomfortable. It's really uncomfortable because like all of a sudden, like I'm sort of definitely an innovator. So I like anything that's innovative. But you know, my more conservative and more well thought out people who are thinking a lot more carefully than I am are like, well, wait, you know, that's not what we meant, you know, we didn't. And so, you know, it's got to be some compromise between innovation and you know, sort of recognizing the nuances between the two situations. But what are people going to use? That's another question. And so, but we were recording things like how often the language, like when the language model comes back with things, we also check whether it's correct or not, like syntactically correct in some way. We were checking all those. Of course, we were finding out that every time we changed the language model, the statistics changed. But it's just like, it's almost like when we started doing genetic programming, we didn't know how to report any of the results. Like the community figured it out over the course of 5-10 years. We came up with these sort of really good, rigorous scientific standards. I don't know what the scientific standards are when you put these things in the box. I just don't know. It's a great open question.
I see more questions, but EC class. I'm afraid we're gonna have to run because this class is starting. So EC class only, everybody else stay here, this room is here.
Yeah, and everyone, we have this group until 11:30, so keep the questions coming.
Yeah, sorry, folks. Yeah.
Everybody else.
It was nice to meet you all. Thanks for your attention.